We talk about minimum shift keying, and we observe that it's a special case of binary FSK, in which case we consider it to be continuous in phase, and that is contrary to what we have seen before with QPSK and OQPSK, in which case the phases were discontinuous. So for that reason, we want to see how we can implement this continuous. The keyword is continuous with FSK, because as you remember, when we are having OQPSK or QPSK, we were having a frequency that was going, and then there is a sudden change in phase. Then you see some other sudden change in phase like that. So this is a typical of discontinuous phase, FSK. And now for the minimum shift keying, we refer to it as continuous FSK, and you see how that happens. So the first stage is to evaluate a binary data stream, BT, that is may be represented as 1 0 1 1 0 0 1 0. So we want to set that bit stream. So this is the one we want to transmit at the TX side. So at the receiver side or outside the transmitter, we are going to have an MSK signal. An MSK signal will be in the form of a wave that is not discontinuous, but it is a form of frequency shift keying. This means that we are going to be having a frequency or a carrier signal whose frequency is changing, but not with discontinuity. So we are going to have sometimes it increases, sometimes it decreases. So if you are to evaluate this very simple frequency that I have drawn, the period between one wave to this one is, you can say it is TB, but the period between this other section is TB, and this one is TB2, is TB1, and TB2 is smaller than the TB1. So what we are simply saying is that we are not going to be having discontinuities, but when we transmit one symbol different from another one, sometimes the frequency will have increased, like in TB2, and it will have decreased in TB1. So let's see how we do that. The first step is to divide the bit stream into odd and even bits. So how do we do that? We enumerate them 1, 2, all the way up to 8, and then we mark the odd ones. We mark them out, and then we are going to say that for the odd bit stream, one bit will be taking 2 TB or 2 bit durations. So the first one was 1. Instead of stopping at this stage, it continues until the end of 2 TB. So for the sake of clarity, between this here and there, that is 1 TB, and between there and there is another TB. So one bit is taking 2 bit durations for us to meet the separation of odd and even bits. So you can see this one goes until the end of the second bit, and then we look at the third bit, which is the other odd bit, and then we say that it has a 1, and this one goes to 2. Therefore, we are going to be counting them as 2. This one carries 2 bit durations, and therefore it is going to be represented as 2 bits of 1. This another one is going to be carrying 2 or to be running for 2 bit durations, so it is going to be considered as 2 ones. So another 5th bit, which is the odd one, is bit 0. Therefore, this 0 will run for 2 bit durations. And finally, the 7th one is a 1 that runs for 2 bit durations. Then we will consider the even bits, and the even bit starts at the second one, so that is where we are going to start them off. And this is when we say that they are shifted by TB. The even bits are delayed by 1 TB, and that is not normal. That is what we expect. If we are going to be considering the bit when it starts, it definitely starts 1 TB after the first odd bit has been transmitted. So we say that this one starts at 0, Therefore, it's going to be having bipolar non-return to zero encoding bipolar, and that means that 0 is going to be having a negative voltage, just like we did with this one. So we have seen that this is 1 bit duration delay, and therefore our even bits start at TB, the second TB. Therefore, we say that this one will take 2 bit durations. So while it was 0, we are going to be counting it twice, so 0 and 0 here. Then the fourth one is a 1, and therefore we are going to shift from, as you have seen, is bipolar non-return to 0. The 1 is going to be represented by a positive voltage. So this is going to be a 1 counted twice. Number 6, or the 6 bit is a 0. We have it represented by 2 zeros here because of 2 bit durations, and the 8th one is also a 0, represented again with 2 bit durations. That is the first step, that is of separating the odd from the even bits. The second step is to know that we are going to be forming a frequency shifted modulation. In that case, our frequency shifting is going to be a factor of bit rate, and we actually say that if the bit rate is TB, then we divide the frequency of the incoming bits by 4. We'll see why 4, and the actual reason is that the end result of the frequency difference between F1 and F2. Remember that this is FSK, therefore we are shifting the frequency. The difference between these two frequencies that we are using to transmit our binary data is going to be equals to a half FB. So if you want us to get a half FB, and FB is the bit rate of the incoming data stream, then we are going to say that if you want to have and we want this separation to be equal, what we are going to do is that we are going to say that F1 plus 1/4 FB minus F4, F2, F1 again. Okay, this is our carrier or center frequency, which is now minus 1/4 FB. We want this to be equals to this. So if we just open this bracket up, this will cancel with that, and then you're going to be left with 1/4 FB plus minus becomes plus 1/4 FB, and therefore this one actually becomes as we want it to be, a half of FB. And this is the minimum frequency separation that can allow us to detect frequency shifted modulated wave. So that is the minimum. That is the reason we call it minimum shift keying. This is the minimum difference between the two frequencies that they can be separated with for us to be able to detect the transmitted bits by the FSK. So having done that, so what we are doing here is that we are generating two frequencies, one with this frequency and the other one 90 degrees apart, and therefore or phase shifted, so that we are going to end up with two waves that are orthogonal or 90 degrees out of phase. So one of them is that we are generating a frequency, a carrier or shift frequency that is of WB/4, and WB is simply 2 pi FB divided by 4. So this is the same thing we are doing. The only thing we are doing is convert this to become omega. So we are calling it omega B. So we know that the cosine wave always starts at 1. So I am running it. So this is the one I'm running. This is the sub cosine, and generating another one that is sine, which is 90 degrees out of phase, and it starts at 0, and that's like that one. That is the first thing. So what we'll do is that we will multiply the cosine wave that we have generated with our odd bits or our odd bit stream, And what we know is that when we multiply a cosine with a -1, -1, remember, is the one that is going to be represented by this. With bipolar NRZ, positive voltage is equivalent to 1 for our purposes, and negative voltage is equivalent to -1. So when you multiply a cosine with a -1, it is going to change phase, and I think we will see this at this point. That remember the blue one, this blue one is the one that are going to be represented by this blue one. So we are multiplying this BT odd times the cosine. So when you multiply this cosine with this bipolar NRZ wave, whenever there is a transition from 1 to 0, we have a transition from positive to negative, and that means this blue wave will change phase to be 180 degrees out of phase. That is what a -1 means. So it will, if we had cosine theta, multiply it with the cosine with the -1, if this is equivalent to cosine of theta plus pi. So that is what we are doing here. That when we multiply our cosine with -1, arising from this odd data stream, is going to shift phase. You can see this shift in phase from it was going up, it was at the center at the top of the wave, to shift changes the phase by 180 degrees. It is now going up instead of going down. So for 2 base duration, it's going to be having that change of phase, and then after that it is going to change the phase again because of this shift by 1. So meaning that there is a change of phase to go back to where it would have been. If we had continued, it would have continued as such. But since now it would have gone back to normal, it remains as it would have been. So this is where we are saying that the change in phase has happened. So similarly, we are going to do multiply the sine wave with the even bits. Remember, the even bits are the ones that we are representing here down. We start at the second TB. So we are going to apply the same principle. When we multiply a sine with a -1 voltage, what we will have, there will be a shift in phase. Assume it started at this point, and we have transitions from to 0, it will change phase by 180 degrees for the 2 base durations. And then there's another phase shift. So it will change phase again by 180 degrees. Instead of going down, they start going up. So this is the one that is represented by black. So similarly, at this point, there is a change in phase from +1 or from positive voltage to negative voltage. Again, the black one changes the sign. Instead of going down, it has a 180 degrees phase shift. Then for the remaining duration, there is no phase shift. It remains continuous until the very end. So that is the step 1. Step number 2 is now to generate a cosine wave that is equivalent to F2 and F1. F1 is the higher frequency component, and F2 is the lower frequency component. So when I was doing F1 here and F2 here, I was considering that F1 is higher than F2. So how can it be higher? It can only be higher if you are adding the WB/4, just like we have demonstrated, for us to be able to get the minimum phase shift. So we are generating our high carrier frequency, and we have a low carrier frequency component. So what we'll do next is to consider these two as die-bit. The one in this bit duration, we have a 1 from the odd, and we have a 0 from the even bit stream. So we are going to count that as 1 0 down there. Again, this is a 1 from the odd bit stream. This is a 0 from the even bit stream. You combine them, you get a die bit representing 1 0. Similarly, this is a 1, this is a 1, you have a 1 1. This is a 1, so this is a 0, a 1, you have 0 1. 0 and a 0, you have a 0 0. That is how we are getting our die bits. And these die bits are now the ones that we are going to use to determine what carrier signal we are going to transmit. So when we have the different bits, when we have different bits in the die bit, we said the low frequency carrier, which is our F2. When we have the same base 0, 0, we said our high frequency carrier, which is F1. As you can see, this one has not changed, so we just submit with the one that was there before, which is the low frequency component. Similarly, this 1, 0 low frequency component, 1, 0 is a different low frequency, but now we have 1, 1. We transmit low high frequency component, which is F1. 0, 1 different, so low frequency. 0, 0 again is high. We said the high frequency component. So that is how we are able to generate our MSK signal. This is our final transmitted MSK signal. You can see we do not have sudden or discontinuous phase. The frequency is continuing. Even if the frequency is changing, the same phase remains. It is just changing in frequency but not in phase. So this is the one we refer to as MSK.